Hi everyone, in this video we're going to continue graphing some rational functions. We're going to see some higher powers show up in some of these, and we'll have to probably do a little more factoring, so we'll just see what kind of mess we get into. Okay, so our strategy for graphing rational functions is we need to find, let me sneak this in, we need to find holes, zeros, and vertical asymptotes. That's our local behavior. And we also need to know our global behavior to get us started. So is there a horizontal or a slant asymptote? You can only have one of the global behaviors, but you could have all three of these local things happening on a given graph. So to find any of these, we need to be able to get the top and bottom in factored form. Let's do that first. The top is an x plus 2, x minus 2. And the bottom, we can factor out an x. Always look for that common factor, so it's an x times x minus 2. Okay, so I hope, if we're all looking carefully, that we see immediately that there's an x minus 2 in the top and the bottom, and I hope you want to cancel it right away. But we have to be really thoughtful about this. This is another one of those pre-calc things where, yes, our algebra skills are telling us to do the right thing, but we're trying to get it one step up now and understand some of the tricky little details that go along with this. So this is great, except if you plug x equals 2 into this one, you get 4 times 0, so 0 on top, over 2 times 0. 0 over 0 is undefined. This one, if you plug in 2, you get 4 over 2, which is absolutely not undefined. So if we really want to claim that these are equal, we have to write down that one exception. They're equal as long as we force the second one to not take 2 as an input. So this is exactly what we're looking for when we talk about finding a hole in the graph. It means the graph will look identical to this function, but we'll leave one little hole, an open circle, so that we skip this single point where x equals 2. So basically, if x is anything other than 2, these factors do cancel out, and you'll get the exact same thing from the 2. If x is 2, then this one needs to skip over that point because that's not allowed, but we won't get any asymptotic behavior because even if the top is getting really, really big or the bottom is getting really, really big, they're doing it at exactly the same rate, so they'll cancel each other out, they'll balance out. We won't go off to plus or minus infinity. Okay, so this does have a hole. The x-coordinate of the hole is 2. This next little bit is something a lot of times people get stuck on or forget, so maybe make an extra note to yourself. You should also be able to find the y-coordinate of the hole. So again, we should be really clear that a hole is a point you don't go through. We're going to skip over it. But we can play around a little bit here and say, okay, well, if I want to know a y-coordinate, I should plug my x in. Unfortunately, if I plug it in here, I get 0 over 0, which is undefined. If I plug it in here, I still get 0 over 0, which is undefined, but I can plug it in here. So what you want to remember is, even though we've just said x is not supposed to be 2, to get the y-coordinate, so to get the y value of the hole, plug in to here. So cancel out the factor that's undefined, that's giving you the undefined when x equals 2, and then go ahead and take the simplified version and plug the 2 in. So we get 2 plus 2 over 2. We get 4 over 2, which is 2. Lots of 2's floating around here. Don't assume in general that the hole will have the same x and y coordinate. It's certainly not something that's true of all of them. So again, if you want to find the y-coordinate of the hole, this is basically telling us exactly where to put this point that we're going to skip over. You simplify the equation by canceling out that common factor, and then you should be able to plug it in. Just be really clear in your head that what you're finding is the y-coordinate you skip, not a y-coordinate you actually go through. So the graph is going to go and pass through that point, but right at that point, we're going to put an open circle and just skip right over it. Zeros. Zeros happen when the top is 0, so we could look at any of these three. Again, you want to be a little careful. They happen when the top is 0 and the bottom is not. So we've already identified that 2 is not a 0, it's a hole. So it may be safest to look at the simplified version to make sure you don't accidentally list the x equals 2 as a 0 or a vertical asymptote. So here, the top is 0 if x is negative 2. And then vertical asymptotes will happen if the bottom is 0 and the top is not. So in this case, if x equals 0, we have a vertical asymptote. Horizontal asymptotes, once again, you can look at any of the three. I would say the first or the last one are the easiest. Once you get it factored, it's slightly harder to see your degrees and things like that. So if we look at the first one, I see second degree over second degree, or the last one, I see first degree over first degree. And either way, I get the same conclusion. The degrees are the same, so it will have a horizontal asymptote. This is the one where you actually have to do a little extra work to figure out what the horizontal asymptote is. So again, looking at either one, here we could think if I plug in a trillion, I get 1,000,002,000,000 over 1,000,000,000,000. That 2 is pretty much negligible. This is really, really close to 1. Same thing here, you'd have a trillion squared over a trillion squared. Both of these become pretty much negligible when you square a trillion. These are all small in comparison. So you'd still have this 1 over 1 coefficient. So this has a horizontal asymptote at y equals 1. Okay, let's see. So if we go to sketch this, hole at 2, 2. So just put an open circle there. 0 at -2. Vertical asymptote is along the y-axis. Horizontal asymptote is right through here, y equals 1. Okay, I think that's all of it. So again, the horizontal asymptote just tells you where to put the arrows. So we're going to have arrows really close to 1 on either side. Could be just above or just below, and we'll figure that out. From here, the first piece of local information I have is that I have to cross through at -2. So my guess is that this thing is just below the horizontal asymptote. And then I come down and I cross through at 2. I know it's a cross through because this comes from this factor right here that has a power of 1. Now, I either have to, the vertical asymptote is next, so I either have to head up to positive infinity or down to negative infinity. And since I don't have another x-intercept, that's going to force me to head to negative infinity. The asymptote also has multiplicity 1, which means, so here it's x equals 0. If you plug in something a little smaller than 0, the bottom is negative. If you plug in something a little bigger than 0, the bottom is positive. So the fraction changes signs. The top, what is the top? The top is positive no matter whether you plug in something slightly bigger or smaller than 0, but the bottom switches. So on this side, we should do the opposite. Our arrow should be headed up to positive infinity instead of down to negative infinity. The hole is local behavior, and you really do treat it like it's a point to pass through, but again, your thinking should be it's a point that I clearly skip over. I get everything right up close, but then I skip it. And then there's no local behavior left to worry about, so that horizontal asymptote will take over. Once more, it's possible if you ever go check graphs of these things, sometimes they jump up above their asymptote and then level off from above, or this one could jump down below and then level off from below. And I'm not super worried right now about you catching those. If you really wanted to, you'd just take the equation and set it equal to 1 and solve, and that would tell you if you ever crossed your asymptote. So it's legal to do, but for now it's not the easiest thing in the world for us to spot just looking at the equation. Okay, next one, we have definitely some factoring to do. We have a second degree numerator and a fourth degree denominator. The top factors really interestingly, it's a perfect square. It factors into an x plus 1 times x plus 1, or an x plus 1 squared. The bottom, the first thing I see is that I can factor out a 2x squared. So always look for those common factors. And that's going to leave me with an x squared plus 2x minus 3. And then I can do a little bit better than that even. 2x squared on the bottom. And that factors into an x plus 3, x minus 1. And this is an x plus 1 squared. Okay, so our usual, we want to look for holes, zeros, and vertical asymptotes. So I see no factors that can be canceled out, which means I don't have any holes in the graph. Zeros happen, the top of the fraction is 0, so it looks like x equals -1. Let me write that the right way. So -1, 0. And keep track of the fact that this has a power on it. That's a multiplicity 2, so we're not going to cross through at -1, 0. We're going to bounce. And then vertical asymptotes will happen when the bottom is 0 and the top is not. So at x equals 0, don't neglect these. If you factor out an x, that means x equals 0 will make that thing 0. So x equals 0, x equals -3, or x equals +1. And once again, we have a power down here. We need to make sure we pay attention to that. So multiplicity 2 on this, which means instead of the two arrows going opposite directions, one positive, one negative, they'll both go the same direction. And it could be both positive or it could be both negative, but they will definitely both go the same direction right next to the vertical asymptote at x equals 0. There's my local. And then the global stuff, horizontal versus slant asymptote. Here, I'm going to go back up to this one. I think this is easiest to spot global behavior. We have second degree over fourth degree, so the bottom wins by a lot. The bottom is 2 powers higher than the top, which means if you're plugging in really big numbers, so if you plug in 1,000,000, you basically have 1,000,000 squared over 2 times 1,000,000 to the fourth. The rest of this, even the cubic, is not very big compared to 1,000,000 to the fourth. So the rest of this becomes negligible. These are the dominant terms. These determine the behavior. So if you have an x squared over 2 times x to the fourth, roughly happening, that x squared can cancel out and it's basically like a 1 over 2x squared. And if x is a huge number, that fraction is tiny. So really, really big denominators make fractions really, really small, which means your horizontal asymptote will be y equals 0. As your x's get bigger, your y values are going to get closer and closer to 0. Okay, so let's see if we can fit this in. So horizontal asymptote at y equals 0. Remember, whenever you have this, it makes it a little trickier to figure out whether you should start above or below the horizontal asymptote. So I'll probably go plug in another point in just a second. I have an x-intercept at -1. I have a vertical asymptote at x equals 0. Let's label this one as well. I have a vertical asymptote at x equals -3. And I have a vertical asymptote at x equals 1. Okay, so to get me started out here, I'm expecting to see my usual little branch of a 1 over x type shape, but I don't know if it should be up above or up or down below. I know I don't cross the axis because there's no x-intercept. Oh, sorry guys, getting a cough again. But what was I saying? Okay, so no x-intercepts, which means I can't cross. So I'll either always be above or always be below. But to figure out which, I just have to plug in a point. So I'm going to try plugging in, let's plug in a -4. Oh, and this is kind of messy. You can plug into a calculator if you want, but I would just say that what we're really worried about is plus or minus. So I'm going to take this factored form, and I'm going to say if I plug in a -4, I get -3 squared, which is +9. I don't even care about the number. You could just put a plus there, but we can write a +9. And again, this is plugging in -4. So if x equals -4, -4 squared is 16. So that's definitely positive. 16 times 2 is 32. And then -4 plus 3 is a -1. And -4 minus 1 is a -5. So I don't care what the number is. It's a small number. What I do care about is the fact that this is going to end up being positive. The negative times a negative will become positive. Everything else is positive. So that means that when x is -4, I have a small positive y value. So I'm coming in close to y equals 0. And I'll head out close to y equals 0 as well. And it looks like I'll be just above y equals 0, and then I'll be headed off to positive infinity. Okay, next, there was only the vertical asymptote to deal with, so this is the piece of information we're working on right now. It came from this factor with a power of 1. So we're expecting to be seeing opposite behavior. This factor will switch signs. So if we plug in something a little less than -3, this will be negative, and we plug in something a little more than -3, this will be positive. So on this side, we're going to head the opposite direction. Okay. And again, it doesn't say one side should be positive and the other should be, it doesn't say which side should be positive or negative. It just says there should be one of each. That's all that odd power says. All the other factors are going to go into determining whether the result is plus or minus. But whatever it is on the left of this asymptote, it should be the opposite on the right. And if you are ever stuck on that or feeling like you're going to mess it up, just plug in -2 and see what you're getting. So the next piece of local behavior is this intercept at -1. And remember, that had a multiplicity too. So I'm actually not going to cross. I'm going to come and bounce off at -1. And then the next thing is a vertical asymptote. So I either need to continue to negative infinity or turn around and head to positive infinity. And because there are no more x-intercepts, that choice gets made for me. I'm forced to head to negative infinity. Oh, shoot. I went too far, though. Be careful. This is actually easy to do. I see students do this too. There's a vertical asymptote along x equals 0, but it kind of disappears into that axis sometimes. So this actually heads like this. Doesn't cross past the y-axis. So ignore. Okay, x equals 0 that I was trying to skip. That comes from this factor right here, and it also had a multiplicity too, which means if we plug in something a little less than 0, when we square it, this factor is positive. If we plug in something a little bigger than 0, it's still positive. This is the one that potentially could change signs there, and it doesn't. So this, which side is this? Right-hand side of this asymptote should also be headed the same direction, which in this case is negative infinity. So again, it's all about same or opposite. It doesn't tell you for sure which direction. It just tells you in relation to the other side whether it'll do the same or the opposite then. I don't have anything else in between, so the next vertical asymptote x equals 1 is the next thing I have to worry about. So the question becomes, do I continue and just head to positive infinity, or do I turn around and head back to negative infinity? And the answer is a turn around. The reason is because there are no x-intercepts, so you're not allowed to cross the x-axis between 0 and 1. So remember that x-axis is a barrier. Almost done. The last thing we need to look at here is the vertical asymptote x equals 1 came from this factor, which is multiplicity 1, which means this factor will change signs at 1. It'll switch from being, let's see, if we plug in something a little smaller than 1, it's negative, and if we plug in something a little bigger than 1, it's positive. So this is going to switch signs as well. So one side headed to negative infinity, the other side heads to positive infinity. And then there's nothing left. There's no more asymptotes, there's no more zeros, so we're just going to let that horizontal asymptote take over. And it's going to look something like this. This is another one where if you check the graph on your calculator, it's possible that this piece is way, way, way down low. So you might not see it. So you have to know that there should be something in between all of your asymptotes. And again, one way to see that is if I ask you for the domain of this, it's all real numbers other than 0, -3, and 1. So you can't skip all the real numbers between 0 and 1. They are in the domain, and there should be y values for those. All right, 2 more. Let's see what's going on here. Second degree over second degree. Okay, so let's get it factored. The top, I'm going to factor out a -2. And I get an x squared minus x minus 6. And on the bottom, I'm seeing an x minus 3, x plus 1. And then I can do a little bit better. I can say -2 times, what is that one going to be? X minus 3, x plus 2 over x minus 3, x plus 1. Okay, so I have a hole again. First thing that jumps out at me here is this x minus 3 top and bottom. I would like to cancel. So this thing can actually be rewritten even more. I can write it as -2 times x plus 2 over x plus 1. And we want to make sure that x does not equal 3 if these two are really going to be identical. So as I start my list, I am going to have a 0. Oh, I'm sorry, I am going to have a hole. I have zeros as well, but the hole was the one we just discovered. And then vertical asymptotes. Okay, so the hole is at x equals 3. And again, remember, this is where a lot of people get mixed up and they do something wrong. If you want to find the y-coordinate of the hole, you want to take the simplified version of your equation where it's actually legal to plug in 3. Here you get 0 over 0, but here you don't. You get 5, -10 on top, and you get 4 on the bottom. So let's see, when x equals 3, y equals -10 over 4, which does reduce a little bit, -2.5, -5 halves. So the y-coordinate of my hole is -5 halves, and I do expect you to be able to find both coordinates, so make sure you remember how to do that. The zeros happen when the top is 0, and again, I think easiest would be to look at this final version so you don't accidentally include the 3 as a 0. When x equals -2, the top is 0, so -2, 0. Vertical asymptote is when the bottom is 0, so at x equals -1. And then horizontal versus slant asymptote. You can look at the first or the last version, any of them in between, but I like the first and the last best for this. So if I look at, I'm actually going to look at the first this time. If I plug in 1,000,000, I get -2 times 1,000,000 squared plus 2,000,000 plus 12. The plus 12 is definitely not impressive when we're talking about numbers that big. And actually even 2,000,000 is not very impressive when you're talking about something with, 12 zeros on it. So the -2 times 1,000,000 squared is dominating the top of the fraction, and 1,000,000 squared will be dominating the denominator of the fraction. So if you have -2 times 1,000,000 squared over 1,000,000 squared, the 1,000,000 squared, that one with 12 zeros, is going to cancel out, and you're going to be getting -2 over 1. So it is horizontal asymptote at y equals -2, which means no slant asymptotes. I'm saving those up still. Right. This paper's getting a little squashed. So we have, what, a whole at 3, -2.5, right here. 3, -5/2. We have a 0 at -2. Oh, hold on. We have a whole at 3. I even wrote it right. 3, -2.5. There we go. -5/2. Don't mind me. Okay, gone. We have a vertical asymptote at x equals -1. We have a horizontal asymptote at y equals -2, so it's just above the hole. Ooh, my line's getting a little crooked. It's important to be careful about whether it's above or below the hole. Okay, so what I'm seeing is, sorry for the mess, we need to enter near the horizontal asymptote, and we need to leave near the horizontal asymptote. So from here, the first thing I have to do is cross through the x-axis. So I'm going to say I'm probably just above that horizontal asymptote. And then I come in, I cross through. Let's just check that multiplicity, but I think that's true. Yeah, it was multiplicity 1, so it is a cross through. And then the next thing, really quickly, I run into this vertical asymptote at x equals -1. The choices are to head up to positive infinity or to turn around and head to negative infinity, but there's not really a choice because there's no x-intercept, so I have to head up to positive infinity. The asymptote has multiplicity 1, which means if I plug in something a little smaller than -1, this will be negative. If I plug in something a little bigger than -1, it will become positive, and the power won't change that. So they should go opposite directions. Anytime you have an odd power, your arrows should go opposite directions. If one heads to the top, the other should head to the bottom. Next thing I have is the hole, so I'm going to work my way up here. And again, you are expecting to see some shapes similar to your 1 over x and your 1 over x squareds. If you have multiple asymptotes, you'll get these funny shapes in the middle that either look like little U's or upside down U's, or kind of like a little cubic. Those are the two things that can happen in between. But always on the ends, you should see these 1 over x type shapes for these graphs. Okay, and again, there's no more local behavior, so the horizontal asymptote's just going to take over. All right, last one on this. Again, I'm going to start right off with factoring. Here, we'll do this down below since we're getting a little cramped. I can factor an x out of the top. I can do a little better with the top, x minus 4, x plus 1. Over x plus 1. So this one also has a hole. I can cancel out the x plus 1. So let's see if we can start our list. Here, we'll do it over here. Hole. So the hole is at x equals -1. So all I'm ending up with here is an x times x minus 4 over 1. When you cancel something out, it leaves a 1, but there's no reason to write over 1. There is a reason to write x cannot equal -1. If these two are really equal, you have to keep the domains the same. To find the y coordinate of the hole, we can plug our -1 back in here after we've canceled. So I get -1 times -5, which is +5. Okay, so we get a hole in the graph. Zeros. We get zeros when the top is 0, and pretty much there's only top now. So if you want to write that 1 just to remind you, you can. So if x equals 0, we have an intercept, and if x equals 4, we have an intercept. Vertical asymptotes would happen if the bottom is 0, which it is not. So no vertical asymptotes. That's my local stuff. My global stuff is horizontal or slant. And the answer here is actually none to both. So we get so submersed in trying to graph rational things and get all these asymptotes that sometimes people get a little distracted about what this is really saying. What I ended up with is no longer rational, it's quadratic. So this is going to be a parabola with x-intercepts at 0 and 4. It would be a positive x squared, so it opens up, and it has a hole. So all this is a parabola with a hole in the graph. If your denominator cancels out completely, you're not going to get your typical rational function shapes that we've been seeing. You're going to get whatever you ended up with holes in the graph. Okay, so x equals 0, 1, 2, 3, 4, and -1, 5 is a hole in the graph. So it's going to go like this. Like this. Okay, so there's my picture. So again, if you don't have a denominator anymore, it's just going to look like whatever you ended up with, quadratic in this case, with a hole in the graph. All right, thanks for watching.